Good afternoon, everyone. Myself Deepak TL and my teammates are the Abhishek MB, Rohit JS, Bhuvan KV. I am here to present ATC project. Our topic is to design and implement a logical operator sequence using recognizer mini ATC. The content of our project include introduction, problem statement, objectives, lexicon analyzer, DFA, context-free grammar, result and test cases, conclusion. Next slide. Next slide. Introduction. The project implements a front-end compiler for the mini-ATC language, bridging the gap between automata theory and practical system. It utilizes the lexicon analyzer to tokenize source code and a syntax parser to validate the structural integrity using a context-free grammar. The goal is to demonstrate how the abstract model like finite automata and a grammar rule ensure code correctness and logical flow. Next slide. The problem statement of our project is the objective is to design a level 3 lexical analyzer and a parser function as logical operator sequence recognizer for mini ATC. The system must enforce specific grammatical rules such as rejecting redundant binary operator example and ensuring not is followed by a validate identifier. This implementation provide automated validation for begin and end block distinguishing between the correct code and the syntax error. Next slide, one. Objectives of our project is token recognition is used to identify the keywords. Token recognition is used to identify the keywords and operate keywords, identifiers and operators. Structural validation implement the parser to ensure a program follow the mandatory block structure and a semicolon termination rules. Pattern enhancement integrate stage-based logic to detect and prevent illegal sequence of logical operators. Error reporting provide clear feedback based on the input programs and compliance with the CFG. Thank you.
Thank you, Deepak. This I'm going to explain the lexical analyzer DFA. This diagram represents the deterministic automata, finite automata used in the mini ATC lexical analyzer. So the DFA starts from an initial state called Q naught, and which is an entry point for recognizing every token in the program. The first section shows the keyword path for the word begins, and the automata reads each character one by one. That is B, E, G, I, N. It takes the single character and finally reaches an accept state, which confirms the keyword is valid. The second section represents identifiers. If the input starts with any alphabet letter, the DFA moves the QID state. This state has a self loop for the letter and digits, allowing identifiers. So such as X, that is value, it will be a temp 1, 2, 3. So the third section handles the logical operator like and or not. So separate transition paths are created for each operator. And once the complete sequence is matched, the DFA reaches the corresponding accept state. The final state recognizes the relation operation such as a greater than or less than or equal operator. Each operator has its own transition path and accept state. So this is the final state which I have discussed. You have correctly used a double circle for all accept states like ID, accept, and which is started into notations in automata theory. So keywords and identifiers. So by showing a specific path for beginning and a general path for identifies a self loop sequence like that, and you demonstrate that a scanner can distinguish between the reserved words and variable names. Next, logical operator. The path for and or not are correctly mapped out. This is a foundation for the logical operator sequence. So logic that you are parser then validations. Relational logical that handles for single character, so that is greater than, lesser than, or double characters, that is a double as a equals operator. It is technically as sound. So thank you. Next, Abhishek continues.
Thank you, Bhuvan. Now I'm going to explain about CFG. CFG stands for context free grammar. It is used in compiler design to define the syntax or structure of programming language. In Mini etc, CFG helps us describe how a valid program is formed. In this diagram is divided into four parts. First one, program structure. This first part explains the overall structure of the program. A program follows follows these rules: program to begin statement list and end. This means every mini etc program must start with the keyword begin, contain one or more statement inside the statement list, and with the keyword end. So this forms the basic structure of the program. And second one, statement definition. The second part explains how statements are organized. A statement list can be a single statement or one statement followed by another statement list. Each statement can be one of four types. First, declaration, assignment, if statement, print statement. This gives flexibility to write different instruction in the program. Third one, logic expression. The third part explains logic expression. A logic expression contain a single logic term or two logic term connected by a primary or binary operator. Rule is logical explorer, logical term, binary, logical term. Binary operators used are and or. These operators helps combine multiple conditions. And fourth one, term and constraint. A logic term can be not identifier or identifier number. Relational operator includes greater than, less than, equals to. For example, x greater than 5. This compares a variable with a number. Code implementation. After designing the CFG rules, the next step was implementing them in Python. The implementation consists of three main components. First one, lexer, means scanner. The first component is lexer, also called the scanner. Its job is to read the input program and break into smaller units called tokens. In this project, the lexer is implemented using Python's re module, which uses regular expression to recognize pattern. Identifiers, keywords like begin and end, identifiers such as variable names, numbers, operators like and or, greater than, less than, and equals to. The lexer also use a state based approach to correctly differentiate between reserved keywords and user defined identifiers. And second one, pairs grammar engine. Its job is to check whether the token sequence follows the CFG rules. In our implementation, we use recursive descent parser. This contains separate functions for each grammar rules such as parsing statements, expressions, and logical conditions. For example, the method logical expressions checks logical expression carefully. It performs look ahead checking to ensure invalid sequence like and or in caps do not appears. This ensures that the logical syntax remains valid. And the last one, error handling logic. The final component is error handling. If the parser finds invalid syntax, a custom syntax error mechanism is triggered. This identifies the exact token causing the error, the location where the syntax rule is violated. This is important for the logical sequence recognizer because it immediately detects incorrect operator sequences and reports them clearly. Thank you. Next part will be continued by J.S.ROHITH. This is important for logic. Thank you. Next part will be continued by J.S.ROHITH.
Thank you, Abhishek. Test results and validation. Case 1 successfully validated positive text. Being x is greater than 5 and not y. And output success. Program is grammatically correct. Signification validates that the phrase correctly handles complex logical string and mandatory blocks keywords. Case 2 redundation operator detection. Negative text input being if x is less than 5 and y ends. Output error redundation report operate sequence detected and significance proves that the significance recognizer logic is effectively filtering illegal grammatical structures. Case 3 valid not follow up negative. Input being if not 10, print x ends. Expected output error not must be followed by the identifier or a nesting expressions found number. Logic lecture identifier 10 if the number CFG rule logic is equal to not identifier rejected anything other than an ID. Case for improves block structure negative input text index x is equal to 5 and expected output error missing being a keyword at a start of a program logic phrase fail the very first step because the program does not start with the required entry terminal. And the conclusion, this project successfully demonstrated that the design and implementation of a robust compiler for an mini ATC language fulfilled all level 3 requirement for a lexical and systematic validation by integrating a deterministic finite automata for a tokenization and text-free grammar for a structural enforcement. The system efficiently identifies and rejects illegal logic sequence such as redundant binary operators. This implements the highly the practicality of automata theory in ensure the code integrity and provides a clear automata error feedback. Ultimately, the project bridges the gap between the abstract mathematical model and a functional compiler logic, establishing a reliable framework for a system directed translation. Thank you.